Hey folks, how y'all doing? It's a little cold in here today, but we have one more section to cover before you finish up chapter 6. And so let's go ahead and get started. I'm going to start with a definition of what we mean by an orthogonal complement. So we're going to start with any subspace. We define the orthogonal complement, which we write as that subspace with a little perpendicular sign after it. And we sometimes, if we are being informal and we don't want to say the words orthogonal complement, we sometimes just pronounce this as W perp. Is the set of all of the vectors in Rn which are orthogonal to the entire subspace, every vector in W. So I'll show you an example on the next page. Here's my example. Let W be the span of the vector 1, 0. So 1, 0 is this vector right here. And the span is all of the multiples of 1, 0. So it includes 2, 0 and 0.50 and negative 3, 0. The span contains all of the vectors on the x-axis. And if we look at the vector 0, 1, that vector is orthogonal to any vector that's on the x-axis. And so this vector is in the set W perp. In fact, every vector that's on the y-axis is perpendicular to vectors on the x-axis, and so the entire y-axis is in W perp. And so that's why we call it sort of an orthogonal complement. It's the subspace that's at a right angle to the original subspace. And we have a theorem that no matter what subspace we start with, the orthogonal complement contains a zero vector, and it's closed under addition, and it's closed under scalar multiplication, but those are the conditions that are required to be a subspace. And so W perp is also a subspace in every case. If you start with a subspace and you take the orthogonal complement, you get a subspace out. And there's one special case that I want to talk about before we move on, and that's the orthogonal complement to a column space. So here's my matrix A. As a reminder, the column space of A is the span of the columns of A. So 2, 5, 3, 7, 2, negative 1, negative 3, 0, 9, and 1, 4, 0. Well, there's a trick for column spaces that we're going to see in a moment. So let's say we have a vector that's in the column space. Because the orthogonal complement to the column space is perpendicular to every vector in the column space, it will be perpendicular all four of these vectors. And so the vector v dot with 2, 5, 3 is equal to 0, and the dot product of v with 7, 2, negative 1 is 0, and so on and so forth. On the next page, I'm going to write this dot product out. I'm going to write this as 2x plus 5y plus 3z equals 0 to get a system of equations. I'm going to write all four of these out. I want to show you the system of equations that we get. We get 2x plus 5y plus 3z equals 0, 7x plus 2y minus z equals 0 from the second column, negative 3x plus 9z equals 0 from the third column, and x plus 4y is equal to 0. But that is just this system. I'm writing this out as an augmented matrix now. The right side is all zeros, so it's a homogeneous system. And this matrix is not A, but it's A transpose. And the solution to the homogeneous system is called the null space of the system. So the vectors we're looking for are the null space of A transpose. And so this is our other theorem for the day, that for any matrix, the orthogonal complement of the column space equals the null space of the transpose. And so we have a way of calculating the orthogonal complement of the column space because we can transpose the matrix and then solve a homogeneous equation. And we will use this fact later today, but I want to move on to something else first. Let's go. All right. In the very first chapter, we learned that a system of equations can have no solutions, one solution, or an infinite number of solutions. What if the system has no solutions? That means for any vector v, a times v will not equal to b. I will not be able to find any vector that I can plug in and make this equation true. But can I find the vector that is closer to being a solution than any other vector? Of all of the possible non-solutions, is there one that is as close as possible to being a solution? What we mean by that is that a times v won't equal b, but they will be approximately equal so that this magnitude is as small as possible. And we call that vector the least squares approximation. A least squares approximation to a system is the vector v such that if w is any other vector in Rn, then av minus b, the magnitude of that vector, is less than or equal to the magnitude of the vector aw minus b. Well, if ax equals b does not have a solution, then the equation always has at least one least squares approximation. And if the columns of A are linearly independent, then we don't have any freedom in the system, and so there is only one least squares approximation. It is unique. So we always have at least one least squares approximation. If there is freedom in the system, we have more than one, but if we don't have freedom, then we still have just one, but it's unique at that point. And how do we find that least squares approximation? So this involves using the transpose again. Suppose that we know that ax equals b has no solution. Then if I multiply both sides by at, by A transpose, that gives us the least squares approximation. And we're going to do an example in a moment. All right. So we'd like to find the least squares approximation to these equations here. So there is no exact solution. And the reason is that I know what these equations say. These equations say that 4x equals 2, and 2y is equal to 0, and x plus y is equal to 11. But if 4x is equal to 2, that tells me x is equal to 1/2. And if 2y is equal to 0, that tells me that y is equal to 0. But then x plus y definitely doesn't equal 11. Uh-oh. And since we don't have an exact solution, we're going to find the least squares approximation instead. What vector is closer to being the solution produces the smallest error out of all the other vectors. All right. Okay. So let's give this a try. We're going to multiply both sides by AT. Or A transpose. So that's going to be 401021 times 400211 x equals 401021 times 2011. On the left side, we solve this using the column row rule. Split this up into columns and this up into rows. So this is 40 times 40 plus 02 times 02 plus 11 times 11 x. And on the right side, this is just a linear combination. It's 2 times 40 plus 0 times 02 plus 11 times 11. Well, let's work this out. This is 16 and 1 is 17. 1, 1, and then 0 and 4 and 1 is 5. On the right side, we have 8 and 11 is 19, and 0 and 11 is just 11. All right. So when we go to solve this, I'm going to start by switching the two rows. So I have a 1 on the top row. And the numbers are going to get a little bit messy, but it will work out nicely in the end. I would need to make this into a 0. So I'm going to take row 2 minus 17 times row 1. So that's 1, 5, 11. 17 minus 17 is 0. 17 times 5 is 85. 1 minus 85 is negative 84. 17 times 11 is 187. 19 minus 87, 187 is negative 168. Then I'll divide row 2 by 2. And that gives me 1, 5, 11, 0, 1, 2. I told you that was going to work out okay. And then row 1 minus 5 row 2. 5 minus 5 is 0. 11 minus 10 is 1. 0, 1, 2. So my solution is that x is 1 and y is 2. And we can check that. 17 plus 2 equals 19. 1 plus 10 equals 11. And so the vector 1, 2 is a least squares solution. Of all possible vectors, it does not solve the original system exactly, but it produces the smallest amount of error possible. So this is the way we find a least squares solution. We multiply both sides by AT, and then we solve. And the solution we get after we've multiplied both sides by AT is a least squares solution, or we can say an least squares approximation. Probably a better word because it's not actually a solution. All right. Let's try another one. Try least squares approximation to this system. So what we're going to do is we're going to multiply both sides by A transpose. So on the left side, we're going to have 1, 2, negative 1, 8, negative 2, positive 1, times 1, 2, negative 1 going down, 8, negative 2, 1, times x is equal to 1, 2, negative 1, 8, negative 2, 1, times 3, 2, 5. The left side is a column row rule problem. So this is 1, 8 times 1, 8 plus 2, negative 2 times 2, negative 2 plus negative 1, 1 times negative 1, 1. And the right side is just a linear combination. 3 times 1, 8, 2 times 2, negative 2, and 5 times negative 1, 1. So this side is, I'm going to write this out, 1, 8, 864 plus 4, negative 4, negative 4, 4 plus 1, negative 1, negative 1, 1. Oh, all right. And the right side is, let's see, 3 plus 4 is 7. 7 minus 5 is 2. 24 minus 4 is 20. 20 plus 5 is 25. All right. So this is 1 plus 4 is 5. 5 plus 1 is 6. 8 minus 4 is 4. Minus 1 is 3. 8 minus 4 minus 1 is 3 again. 64 and 4 is 68, and 1 is 69. Oh, wow. So let's see what we can do with this. Switch to 2 rows here. All right. Yeah, let's do that. 3, 69, 25, 6, 3, 2. Get rid of that 6 by taking row 2 minus 2 times row 1. All right, so 6 minus 6 is 0. 3 minus 138 is negative 135. And 2 minus 75, no, 2 minus 15, excuse me, is negative 48. All right. This looks like fun. All right, divide by 135, and we get 48 over 135. I can take out a 3, and I get 16 over 45. All right. Let's try this. Get rid of this 69 here. So row 1 minus 69 row 2 is going to give me 3, 0, and then this last term is going to be 25 minus 69 times 16 over 45. 69 times 16 is going to be 1004. So that's 25 minus 1004 over 45. It's got a common denominator here. 25 times 45 is 825 plus 300 is 1125. And that's 121 over 45. All right. And then divide the top row by 3. And so we get 121 over 135 and 116 over 45. And so my least squares approximation looks like 121 over 135 and 16 over 45. And I sure hope I have made a typo somewhere, because that's an ugly answer. All right. Let's move on. How come this works? So let's say we have, let's go back here, these two vectors here. They generate a plane, and all of your linear combinations are in the plane. My vector b that we're charting here, which is the right side, isn't in that plane, and so no linear combination of v1 and v2 are equal to b. But the smallest error is going to be right here, where the difference between these vectors is perpendicular to the plane. So this vector p, because it is in the plane, it will equal ax for some input vector x. And the difference between b and p is going to be orthogonal to the plane, which means it's going to be in the null space of AT. Because, again, P is in the column space, and BP is orthogonal to the column space, so BP is in the column space perp, which we saw at the beginning of the video, is equal to the null space of AT. But that means if I take AT and apply it to this vector, the answer has to be 0. Because this is a vector times a vector that's or matrix times a vector that's perpendicular. It's going to be in the null space. The answer is going to be 0. But P, remember, is in the column space of A, so it's A times some vector X. And so these are equal. And if I distribute the AT and move one term to the other side, I find AT times AX equals ATB, and that's the equation that we've been solving. This equation always gets us the least squares solution using the fact that the perpendicular direction to a column space is the null space of a transpose, and that's why we have to use the transpose to solve this problem. Anyway, that's it. Let's do a couple of true-false questions just before we move on, because you never know what's going to be on the test. Every orthonormal set of vectors is linearly independent. Well, that is true, because every orthogonal set is linearly independent. And I see that I misspelled orthonormal. There should be an R in there. I'll fix that later. Every non-zero subspace of Rn has an orthogonal basis. That is true. All subspaces have a basis. I should say all non-zero subspaces have a basis. And all bases can be made orthogonal. Using what we called last time the Gram-Schmidt process. So you combine these together, every non-zero subspace has an orthogonal basis. All right. If W is a subspace of R3 and the projection of a vector U onto W is the zero vector, then U itself is the zero vector. This is false. Um, we have two vectors, and so they generate a plane. And my vector U could be exactly perpendicular to plane. So that when I project it down onto the plane, I just get a single point that has no length, and that would be the zero vector. And so that is the projection of U onto W. Um, so U may not equal the zero vector. This is false. One more. If the columns of a matrix form an orthogonal set, then the matrix is invertible. This is also false, because to be invertible, the matrix has to be square, and this might be true, but A might not be square. If it said that the matrix was square, if this word was square, then the answer would be true. But without that word in there, the statement is false. All right. Y'all take care. I'll see you around.